Alright, so here we are. We've made it to mission 4. Here are the problems I assigned in mission 4. These guys. Alright, and let's get to it. So, problem 7.4. I love this problem. I love this problem a lot. Like, it's beautiful. It's just beautiful. So you're supposed to show that the derivative of the determinant of in plus ta is equal to the trace of a. And then you're supposed to show this identity down here. So I just calculated it. All right, and when I say I just calculated, I mean I used the proper way of looking at the determinant, as well as some things about calculus that you may or may not know. So first of all, this is a formula for the determinant of I plus ta. Sum over all indices. This is the completely anti-symmetric symbol. And what we're doing is we're taking the first column, the I1th component, the nth column, the inth component. All right. Now, this I can rewrite as the product of these n columns. That's a notation for product that just saves me writing. All right. Now, if I take the derivative of this, well, first of all, this is constant. This is either -1, 1, or 0. So I can pull those out and pull the sum out because the derivative is linear. And then this term right here is the extended product rule. And what's going on here is we're simply taking the product of everything except for the kth term, and then we're differentiating the kth term. We take the sum over all of those. This is the extension of the product rule to k-fold products. Now this just differentiates to the kth column because derivative of t is 1, and then we've got that. But the thing is, I can pull the sum over k out front because this and that sum are independent. N is the fixed dimension, the size of the matrix here. And as such, you get this is that, but again, we're evaluating at 0, so that drops out. And you've just got this, which you can recognize as the determinant of everything being the standard basis except for the kth column, which is A. And if you think about that determinant, it's easy enough to calculate that it gives you AKK. As such, you've got the sum k equals 1 to n of AKK, also known as the trace of A. Yay! So that is a really different way of calculating this identity than we just saw out of the solution based on Lawrence Conlin's book. All right, so that's kind of neat. And then part B is easy once you have part A. Like part B, if you follow the hint, it is not bad. So part B here. Let's see here, getting to the point. Since the determinant is continuous, we can find gamma of t is equal to x plus tb. Takes values in GL and R for t sufficiently close to 0, since gamma of 0 is x, and the determinant of gamma of 0 is non-zero. All right, so the determinant has to stay non-zero for t sufficiently small is the point by the continuity of the determinant. And so gamma prime of 0, of course, is b, and we can calculate the differential of the determinant at x acting on gamma prime of 0 is the determinant of the composite with gamma prime of 0. But we can calculate this composite of the determinant composed with the curve. We get this, which if we pull the x out, as we can because x is invertible here, we'll get the determinant of x times that determinant. And consequently, we derive that we've got the derivative at 0 to be the determinant of x times the derivative of this. That's a constant, so it pulls out of the differentiation. And when you differentiate that by the previous problem, you get the trace of the matrix multiplying t. And that's what you're trying to prove. Actually, there it is, right there. So, yeah, that's just pretty. That's just pretty. Now, this shout out to my brother. I was starting to do something foolish with conjugation here, and there is a conjugation-based argument. So to prove a subgroup is normal, one way you can do is you can prove the left and the right cosets are equal. Right, every left coset's also a right coset, like those match up. And if you don't know what that means yet, that's okay. That just means you haven't had abstract algebra. But in any event, so you look at the connected components, which we should know from topology, hopefully by the end of the semester. But if not, that's okay. Connected components are the maximal any topological space, you can break it up into connected components, and these partition the set. They're disjoint sets, which are connected. And so if we have G naught as the connecting component of the identity, if we pick any H in G, then we can notice that H is in the left coset given by H, and it's also in the right coset given by H, because H is equal to and he. And hence H is in both, but the thing is, H and the left and the right cosets, they're both images of the connected component containing the identity under the diffeomorphisms, LH and RH, which, and we know that the homeomorphism, and we quote unquote know, from topology, we know that the homeomorphism must map components to components. Thus, it follows that G naught, that means normal subgroup of G, which is half of what we're trying to prove. And if we have H naught is a subset of G is open, then H naught's a neighborhood of E, and then by proposition 7.14, H naught will generate G naught, which means H naught must be equal to G naught. And so essentially, if G tilde is a connected component of G, then if X naught's an element of G tilde, then the left multiplication of G naught is X naught G naught equal to G tilde. Hence, G tilde is diffeomorphic to G naught. So that's it. And my brother's also talking to my brother about this, and he's like, well, there's also an argument from, if you look at, the other way to show a subgroup is normal is to prove that it's invariant under conjugation. So like to show that H, say H inverse G naught H is equal to G naught again. And you could accomplish such using the path connectedness and looking at a loop and so forth. That might be the solution you might see in a book somewhere, but this is a good solution. I'm just going to leave it here. There is another solution to find in terms of loops, though I will say that. Now, excuse me. So here we go, problem number 37. We're supposed to show that this defines a smooth transitive left action of invertible n+1 matrices on real projective n space. Now, RPN rather. And so I don't even deal with the smoothness. Like, you can prove the smoothness if you want. I'm not going to worry about that. I'm just going to focus on the axioms for the group action. And so it's pretty clear that if we have this, well, the proofs are just calculations, really. Like, not much to say here. So first of all, this is the line with direction vector x, right? That's what the points are in RPN. So if we take the identity matrix, we get back x. If we look at a dot b dot, line with direction vector x, we get ab acting on the line with direction vector x. So it satisfies the basic axioms. Now, so it remains to show it's transitive. And so if we pick 2 points in RPN, right, which is to say 2 lines in Rn+1, then we need to find a n+1 matrix which maps this to that. Now, it'll suffice, though, if you think about it, to find an invertible n+1 by n+1 matrix that maps x to y. But we know how to do that, right? So here's the usual construction. Oh, man, if blah. I was going to write something back there. Oh, man. What's supposed to go there? I'm not thinking. If blah, then blah. Oh. I'm saying if the one vector is a scalar multiple of the other, and let's see here, I want kx equal to, so y. Oh, come on, come back to me. Well, that's annoying. Maybe this one won't. Come on. Hopefully you got some life left in you. There. If y is equal to kx. All right. So that would be the case that oh, oops, I just realized there's a hole in my video earlier. Oh, man. Oh, Anyway, so if that is the case, then of course it's easy because you can just do a multiple of the identity to map the x to y. And otherwise, you can do the basis extension trick, right? You take x and y, put them in a basis, extend that thing like so. And with respect to that nomenclature, we have x maps to E1, y maps to E2, and so if I let B be the matrix that has E2, E1, da da da, that this matrix is the matrix which maps E1 to E2, then AX will be equal to Y, and as such, and also A will be invertible by construction, and there you go, that proves we got a trans. So basically the transitive action proof here is a simple adaptation of the thing that I asked you guys to do at the end of class one day, and I forgot to circle back to. So it is important. This is like a pretty important calculation, I would say, in the big scheme of, interesting applications of linear algebra. Because I don't think it's altogether obvious, and I get stuck on it if I forget. And it's pretty hard to derive directly, in my experience, being, not that bright. So SU2 diffeomorphic to S3. Basically, the proof for me here falls out as soon as I come to a proper formulation of S2. Like if I really dig down and see what it is. So SU2, special unitary 2x2 matrices, complex entries, Hermitian conjugate is the inverse is what this means, right? So if the Hermitian conjugate is the inverse, then that gives us that like A star, it gives us the Hermitian conjugate, which means we transpose and we conjugate. And the inverse is what it is. Of course, the determinant being 1 makes this formula much nicer because we just got, D minus B minus C and A. And so lo and behold, we've got this these equations. So, and so. And if we put in real content, then we see that the pattern of the matrix is this. And once you write that down and you realize that the determinant of the matrix is the length of A1 plus IA2, comma B1 plus IB2, if you think of it as a 4-vector, it just becomes obvious that the diffeomorphism here is going to be this maps to that, and the inverse is clearly that. And it's smooth, it's invertible. So okay, so F2 is diffeomorphic to S3, yeah. Hooray. Now, if you don't drill down into what SU2 looks like, then that will be much harder. Let's see here. Problem 8.3. Not that this is wrong. I just gave up on the technical blah, blah, blah. So, I'm trying to produce a set of vector fields which is, countably infinite, because that's the easiest thing to do. I think this is actually uncountably infinite, but anyway, so if we have a manifold, then of course we've got the coordinate frame. But you can basically, the thing that makes it infinite dimensional is you can take the coordinate frame and you can multiply it by a smooth function of your choosing. But the thing is, there exist infinitely many linearly independent smooth functions. So I think the cleanest thing I came to, and this probably could be simpler. There's probably a simpler way to do this one, but this is what I used. I'm going to let my set S be x1 to the nth power, partial x1. That is available to me in any manifold of positive dimension, right? And the thing is that you can prove that this is linearly independent as a set of vectors, vector fields, because when you hit this, take a linear combination of this, a finite linear combination of these guys, and set it equal to 0. If you act on x1, then it gives you the same problem as the linear independence of the monomials in a variable. But we know that that's linearly independent from linear algebra, so yay. And if you have a linearly independent set of arbitrarily large size, that proves it's infinite dimensional, right? So yeah. This one here, we have a map M from the first quadrant rather, and we're just supposed to calculate the push forward under F under this map. And so this is pretty much a calculation, and but this one since it's a diffeomorphism, we can actually use the formula in the book to do the calculation. I don't always do that, I guess. But anyway, so I calculate the Jacobian. It's everywhere non-zero, so then I find the inverse map somewhere in here. Let's see here. Bop, 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 bop. Oh, okay, then I'm proving it's injective and it's onto. And the trouble of proving it's onto, I just decide to go ahead and calculate the inverse, because once you know the inverse exists, onto becomes stupid. So solve that for x and y, and I do that, I get x equals that, y equals to that, and beep bop, beep bop. So my inverse map is such, and as such, you can easily prove onto. Great. And then I'm following example 8.20, which makes use of the push forward under f of x at q is df at f inverse of q acting on x of f inverse of q. Blah. And I just, basically what I do is I find the Jacobian matrix of this, and then I plug in the point xy with the point f inverse of uv, which gives me this. And also, if this is the vector field, then here's the vector field at that point. If this is the vector field, then here's the vector field at that point. And so then to calculate the push forward, I just do basically this times, all right, so like to get x, what I'm doing is my coordinate vector essentially is this, that, so I take this, that, put it here, multiply by that, and that gives me this for the first one, and that for the second one. I'll let you guys look at the pattern. There's a pattern here. I think I explain better on the next page. But anyway, there's what it works out to for me. Well, of course, you guys can come talk to me about any of these if you're curious. Just make sure I'm not too tired from physics, because I'll say stupid stuff. So anyway, that and that. So this is what I was doing the last page. Basically, I'm taking the Jacobian matrix times the coordinate vector for the y, and I'm multiplying those. That gives me the the things I want to put next to the output, uv and minus v squared over here. So all right, anyway, so okay, great. That's how the book calculated it, and I can calculate that just the same. And how do I usually calculate? Is I just sometimes I do this, like partial f1, partial x, partial u, partial f2, partial x, partial v, like this. Is, I just, this is how I calculate the differential directly. Where here, of course, f1 and f2 are the coordinate function, the first and second coordinate functions of the big F map. And as you can see, going through the calculation, I get the same answer. All right, and ultimately, to get this answer, I do have to know the inverse in order to convert the x's and y's here back to u's and v's. So yeah. I don't know. It's not really a different calculation. That's just how I look at the calculation. I don't tend to think of the book's way of doing it, but maybe I should. I don't know. But so here, I'm just this time I'm redoing it with direct coordinate calculus. So this is that, but that's this, which gives me that. All right. So you can compare and contrast my way of calculating to using the book. I said writing x and y in terms of u and v requires we know formulas for the inverse, and I found the formulas by solving this for x and y. Certainly we can calculate df x when f is not invertible, but if f is not 1-to-1, then you might put in a vector field and not get one back out because of the issue of not being single valued. All right, problem 41, I'm not going to say too much about. It's just straight calculation. Now, I will say this. You can just straight calculate like that, and of course, the second order stuff has to cancel out because we have to get, again, a derivation. As an output, we have a theorem that the Lie bracket of two vector fields is a vector field, right? So you can't have second derivative terms because, as we proved, second derivative terms on their lonesome without another second derivative term to cancel out is not a derivation. And as such, it's not a vector field. Now, the other way you could calculate this would be to calculate the components of the Lie bracket, this, that, and just multiply by this, that, and that. And so in some sense that's easier because these are easier calculations, bang, 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 which gets us the same answer. So you can kind of contrast my two different ways of doing part A, see which you think is better. However, I would point out that in like part B, I did my component way to start with, bang, 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 answer, right? And the alternative way, just like explicit calculation on a function, you find the pattern and then get rid of the function at the end. That's a really kind of different way of calculating. But also, if you're if you're lazier than I was the first time, or maybe smarter, you can simplify it and not write so much because you're only looking for the terms which are going to give you a first order term. So as you look at this, like I don't even need to think about like this one acting on that one, for instance, because it's necessarily second derivative. But this one acting on that, that's what I'm interested in because the y hits the y and just leaves me an x partial z, which is that term. And down here, like this, acting on that, I don't even need to think about because it's going to give me like a partial z partial y, which is not the second derivative. But this acting on that, I also don't need to think about because it's going to give me second derivative. This acting on that, second derivative. This acting on that, well, the y hits that makes the derivative go away, and we get plus minus minus minus, which is minus z partial xf, which is this term. Now, of course, I am skipping over a myriad of product rules in that logic, right? But if you become disciplined about not missing things, you can go through this calculation far faster than I was making explicit on the previous page, and so that has value. And then, so I decided that's the fastest way, so for part C I just got this. And you can check me, I haven't double checked this, is the one I haven't. I calculated the other two different ways, so I'm pretty sure I'm right. Or I'm wrong twice the same way, which would be unusual. But this one I only calculated once. So if you get a different answer, let me know. Actually, turn your homework in when I come up. I guess I could just go check. At least one of you turned it in. Proof that it is a Lie algebra is pretty straightforward. You need to show it's bilinear, antisymmetric, and satisfies the Jacobi identity. Bilinearity and antisymmetry are standard, identities from Calc 3. The Jacobi identity is in my Calc 3 notes, if you can just quote my Calc 3 notes, but the other way to prove it directly is to remember the so-called back cab identity, which I've written as ACABA, ABC, which is that the triple cross product as such is the dot product of A and C with B minus the dot product of A and B with C, like so. All right, so then if you calculate this and that, it gives you these 6 lovely dot product times vector terms, which come in canceling pairs, which gives you 0, and therefore it is a Lie algebra, because it is satisfying the axioms of the algebra. Now, this here, I feel like we're missing a little Lie algebra theory to make this problem not obnoxious. But essentially the story is this, is because we're in the context of the Lie bracket here, we automatically have the bilinearity and we automatically have the antisymmetry. We automatically have the Jacobi identity actually, because this is all happening under the auspices of the Lie bracket, which does give us a Lie algebra structure on the set of smooth vector fields on R3. So it really just remains to prove that the bracket is closed under, that we have closure of the bracket under the spanning set for A. Now I say a little bit more here. I basically say, well, you can basically define the Lie algebra on A by extending, off the bracket linearly, but whatever. Anyway, so I just calculate here. And the calculus shows that the bracket of x and y and x and z and y and z is, again, minus z, y, and minus x respective. So the pattern is very similar to the cross product for R3, but not quite, because I have x cross y hat is z hat, but I have y bracket x is z. So I would like for the isomorphism just to be vector ABC maps to ax plus by plus cz. But unfortunately, that's not quite a Lie algebra isomorphism, because I don't preserve the bracket. I get minus the bracket. So this is like an anti-homomorphism or something. Now it is a bijection, so I might as well say anti-isomorphism. However, you can define a different Lie bracket structure on the smooth vector fields. You can call it the opposite bracket. Opposite bracket of x and y is just y and x. This is kind of stupid, but you can check that this is bilinear, antisymmetric, and satisfies Jacobi, and as such, it is a Lie algebra on smooth vector fields. And so, since that is isomorphic to the standard Lie bracket, and it's pretty clear that the cross product is isomorphic to the opposite bracket Lie algebra on the smooth vector fields, then by transitivity of isomorphism we have the desired outcome. So yeah, that's a little bit uglier than I wanted it to be. Sorry about that. This one here, we're supposed to just prove that the F star is an isomorphism of Lie algebras. So this I'm just reinventing the wheel here. I mean, these are good calculations to understand in terms of for a left invariant vector field, we push forward the value of the vector field at the identity by the left translation maps to get things everywhere. But basically, the long and short of this is I don't really understand why this Homer problem is. It seems like there's nothing to it, because proposition 8.30 gives us that the push forward is a homomorphism. And if you say it's a local diffeomorphism, then that means that the push forward is a locally it's an isomorphism at each point. I guess that's the thing is then, so if it's an isomorphism at the identity, then because of the structure of left invariance, you get it everywhere. But here's my arguments. I'll let you look at them. I don't want to say any more here at the moment. I'm not entirely convinced this is a proper solution, but it's what I got at the moment for you guys. I think this could be cleaned up, is what I'm trying to say. I'm not convinced this is clean as it could be. Here, 45, we have determinant is a Lie group homomorphism, calculate its induced Lie algebra. So yeah, I mean, this is pretty much just a straight application of problem 7.4. The push forward to the determinant map is at the identity of B is the determinant of I times the trace of I inverse B. But hey, that's just the trace of B. Hence the determinant push forward is exactly the trace. And here I'm using that the tangent space at the identity of the Lie group is the Lie algebra. All right, so we do have this, like, we can either talk about the Lie algebra being the left invariant vector fields, which is at times convenient, but I oftentimes find it more convenient to say that the Lie algebra, the Lie group, is the tangent space of the identity. And you can do that because they're isomorphic. All right, so, and so here, the last problem, we're supposed to actually calculate the the structure of the Lie algebra for every one of these matrix Lie groups. All right, and so for every one of these, I'm going to use that the Lie algebra is the tangent space at the identity of G, and I'm going to study curves through Ein's element I, which is the identity here. So we don't usually get to say Ein's element, but anyway, I just thought I'd inject it to wake myself up. All right, so there we go. So here's SLN. since I is an SLN, by continuity of determinant, there exists some epsilon such that alpha of t, I plus tb, is an SLNR for all t in that, plus or minus epsilon set. And since b is the derivative of alpha at 0, it must be that that's in the tangent space of the identity to SLNR. But then we can use problem 7.4, which tells us the derivative of the determinant of this is the trace of b, but this is given to be 1. Derivative of 1 is 0, so we get 0 is equal to the trace of b. So apparently the tangent space to the identity of SLN, big SLN, is the traceless n by n real matrices, which is called little SLN. The little s is for the Lie algebra, the big S is for the Lie group. This is the standard nomenclature, standard terminology. So next up, SON. So again, I'll let you guys look through these, but basically the argument, every one of these arguments amounts to write a curve at the identity. Notice that, and the curve has the form I plus TB, and then that will put B in the tangent space to the identity. And then we use the defining condition for the group and the problem 7.4 trick as appropriate. Now this one here, you get that the condition on the tangent space identity is that the transpose is equal to minus the matrix. That makes B an antisymmetric matrix. It turns out that because of this calculation right here, antisymmetric matrices are automatically traceless. And as such, we don't even need problem 7.4. We get that the determinant of alpha is, we get the traceless condition independent of the determinant. And this isn't really surprising because if you're in the, if you have the condition A transpose A equals to I, either you've got determinant of plus or minus 1. But this is why the name is given to be, the Lie algebra is given to be ON, because that's actually the Lie algebra of big ON, which is the orthogonal matrix group. So the Lie algebra of SON and ON is the same. It's just traceless, it's the set of anti-symmetric n by n matrices. And then complex, then we're into the complex examples. And this time we do some soul searching. We realized that problem 7.4 could equally be known for complex matrices, and we still have this. And so the condition for complex SLN is simply traceless again. So the SLNC is just a set of traceless n by n matrices. And very similarly, the unitary matrices that satisfy A dagger A equals to I, A dagger being the Hermitian conjugate. Well, anyway, the Hermitian adjoint, I don't know whatever you want to call this thing, it's the transpose conjugate transpose. And so once more, we differentiate the defining condition of the group for the curve that goes through the identity, and as such, we derive a necessary condition on the velocity vector to that curve, namely that it is an anti-Hermitian matrix, that the dagger of B is equal to minus B, all right? And that makes that the tangent space to the identity, which is called little un. This time, un and sun do not have the same Lie algebra, because it turns out that it is not automatically the case that being anti-Hermitian necessitates that the diagonal of the matrix is identically vanishing. You just get that it's pure imaginary, so it's not 0. And on the other hand, sun adds that additional determinant condition, which just forces the traceless condition, in addition to the skew Hermitian condition on the Lie algebra. Now, the other thing to mention is if you're reading physics, be careful, because when they exponentiate the Lie algebra, they tend to put a factor of I next to their Lie algebra, which messes up the reality conditions and stuff, but that doesn't really matter for this course. I'm just saying there are some different conventions used for Lie algebra and the exponentiation of the Lie algebra as it relates to the Lie group because of quantum mechanics. And then finally, problem 46, another way to look at it would be like I told you guys with the matrix exponential. In that case, we could let the curve be gamma of t is e to the tb, in which case you'll get, identity is for 0, and again, gamma prime will be b. And we calculated the derivative of the matrix exponential as b times b to the tb. And in this world, we need the identity determinant of e to the b is exponential of the trace, which can be derived using Jordan form, but it's not particularly a simple matter. It's easy if b is diagonalizable. It's pretty easy to derive this. If b is not diagonalizable, then it requires the machinery of the Jordan form. So it's a bit bit much, but it's still true. In general, for any matrix, this is a general identity. And that is our route from determinant 1 to getting traceless. So either you got to derive this, or you do the problem 7.4. Anyway you slice it, getting at that traceless condition, or you need the sneaky argument in Conlin, which is by far the least technical of these arguments. It's a masterful calculation, really, in retrospect. But anyway, there's different ways to get at this traceless condition. Yeah, so you got two options, basically. You can either use alpha of t as I plus tb and the problem 7.4 to pick up on the traceless condition, or you can use gamma of t as e to the tb and that to analyze the structure of the Lie algebra as it relates to the Lie group. Now, the exponential, I think Lie gets to that in like chapter 20. So anyway, hey, that brings us to mission 5. Woohoo!